So this is a session that we're going to look at trends in the periodic table, but specifically look at the halogens. Now, obviously, there are some things that link to other groups in the periodic table, but we're going to focus specifically on the halogens, and we're going to look at group 7, which is the halogens, atomic size, and what the trends are in terms of atomic size, trends in terms of electronegativity, trends in terms of intermolecular forces, and then we're going to look specifically at some of the reactions of halogens. If you are an EdXL student, again, feel free to link back to your specification. These are the points that we're going to try and cover. We won't be able to cover everything, obviously, in all the detail for all of the different exam boards, but we will do our best to cover the majority that fits across all three. And as you may have already seen, if there's any discrepancies, we will let you know, any major discrepancies. If you're AQA, then it's these spec points that we're going to be looking at, and OCR, it's these. So I just thought I'd spend literally 2 minutes just talking about the periodic table, because you'll notice here that we'll use the periodic table, but I'm not going to use the visual of the periodic table as much. So back in the first session when we talked about exam technique, I spoke about the periodic table being one of the best resources that you can use, that and the specification, but the periodic table is given to you in your exam. So as much as the more of your revision that you can relate to the periodic table and that you can use the periodic table to remember things or to understand things or to apply things, etc., the easier you're going to find it, because you're given the periodic table in the exam. So just a couple of things, if you weren't sure, a couple of things that you could look to connect to the periodic table is things to do with trends, obviously, in the periodic table, seeing how they fit with the periodic table, bonding and structure, because that's hugely related to the periodic table in terms of metals and non-metals, gaining, losing electrons, formation of ions. This is all to do with the periodic table. Electronegativity, you can link to the periodic table. Size, you can link to the periodic table. Our transition metals can be heavily linked to the periodic table as well. Electron structures, you can use the periodic table. There's loads, and there will be more. I've just forgotten them immediately off the top of my head. So there's loads that you can do that uses the periodic tables to help with revision. So I really, really would recommend create yourself a big poster with a periodic table in the middle and link everything to it if you can. That's what I would do, or something like that. But right, let's focus a little bit on our halogens. So hopefully we know the names. Group 1 elements, we call them alkali metals, because they become an alkali, they form an alkaline substance on addition to water, sorry. So that's why we call them alkali metals. Group 2, we don't really have a name at A level for group 2. We just call it group 2. Group 7, we call the halogens. And then group 8/0, we call the noble gases. So you can refer to them as either of those names in your exams, and they may be referred to as either as well. We do need to know what we're talking about. So group 7, that is our halogens. That is, oops, sorry, my pen's turned itself off. Let's turn it back on again. Group 7, that is these guys here. We haven't included the bottom, most recently named elements, but so that's group 7 down there on the right hand side. These are the halogens. Now I personally do try my best to be very specific with the keywords I use. I'm obviously not perfect, nobody ever is, but I do my best. So when I'm talking about a halogen, I'm talking about the neutral form of the element. If I talk about a halide, I should be talking about the ionic form. So I will try my best to be specific, and you guys should be as well, because in an exam, they will expect you to be. So halogens are group 7, lovely. So you need to know, and it says so in the specifications, you need to be able to recall the formula and state of the halogens at room temperature and pressure. Now, most of them don't call for fluorine, but we've included it anyway, because you might as well. But chlorine, bromine, and iodine, definitely you need to know the state and colour across the exam boards. So what are they? Hopefully all know from GCSE that the halogens are part of that little kind of upside down L shape on the periodic table, which form diatomic molecules. So di meaning two, atomic, two atoms, two atom molecules. So F2, Cl2, Br2 and I2. Similar to oxygen, which is O2, nitrogen, which is N2. So that's our little upside down L shape. Again, a link to the periodic table. You don't have to remember those 1, 2, 3, 4, 5, 6 individual things and hydrogen, 7. You can remember the upside down L with hydrogen. So that's only 2 things you have to remember instead of 7. Where did I go with that? Diatomic. So they're all diatomic. Hopefully we already know they're all diatomic. Fluorine is a pale yellow gas. Okay, actually, I'm going to try and do them coloured. If you can't, you might not be able to read it. I'll do my best to. Oh no, that's going to be not very easy to read at all. Let's try a bit better. Pale yellow. Fluorine is pale yellow. Pale yellow gas. Chlorine is a pale yellow green gas. At room temperature and pressure, sorry, this is at room temperature and pressure, and you need to know these off by heart. Bromine. Let's see if I can get, I don't really have a brown, I've got orange. Bromine is a brown liquid at room temperature. And iodine is, and they do vary what they want you to say, but mostly they're happy with black, but do double check because sometimes they're expecting you to say a blackish purple. Or sometimes they will even accept grey, but I believe that's only at GCSE. So I think at A-level, we need to be saying black or blacky purple or very dark purple. But again, this is one of the things that does vary throughout the internet and across exam boards. So just double check that you're happy with what yours is expected. What is expected from you, sorry. And then let's just give them all, oops, pen. So fluorine, oh, sorry, I thought I changed that colour. Let's go back to blue. Fluorine is in the gaseous state at room temperature and pressure. Chlorine is also gaseous, but then bromine is liquid and iodine is solid. Something also to note about iodine, the other reason why sometimes they're happy with you to use the word purple is because iodine sublimates, so it goes straight from the solid state to the gaseous state without going via the liquid state. So it sublimates, and the gas that's produced, the gaseous form of iodine, is actually a lovely purple colour. It's beautiful if you've seen it. Really, really nice. But that's why sometimes they will accept purple. Or sometimes where you might see it written as purple. Okay, let's have a look at them forming compounds then. So group 7, they're group 7, which means they're over on the right-hand side. They are non-metals, or what we would class as a non-metal. And when they react, so all things react, all chemical elements react to produce compounds or molecules or whatever it is that they form, whatever they react to gain a full outer shell of electrons. That's why our noble gases, group 8, don't react, or group 0 don't react, because they've already got, or they're very inert. They do react eventually if you force them to, but they're very inert, they're very unreactive, because they've already got their full outer shell of electrons. So if they've already got a full outer shell of electrons, they don't need to react. Other elements react to gain that full outer shell of electrons, because that is their most stable configuration when they've got a full outer shell. So what do our halogens need to do to gain that full outer shell? They have to gain 1 electron, which is fairly easy to do because it's only a single electron. So single electron, it needs to be gained. Because it's fairly easy to do. By the way, easy, I mean low energy. It doesn't require much energy to gain a single electron, which means it can happen rapidly. It can happen easily because it doesn't need much energy. So this makes them highly reactive compared to lots of other elements. So it's all relative, but highly reactive compared to other elements. Halogens therefore form 1- ions, and we call negative ions anions. So they form 1- anions. Usually, we will look briefly at when there's a slight discrepancy within that description later on. But you need to be able to draw your dot and cross diagrams to show the formation of these ions. So how would you edit these atoms to become the halide ions? What would we do? Well, both are going to gain one electron. It's going to gain an electron next to the unpaired outer shell electron. So I'm going to do it as a cross because I'm showing that that electron has come from elsewhere. And if my fluorine atom has gained a negative charge, well then overall, that species will have one negative charge. It's got atoms have an equal number of protons and electrons. Protons are positive, electrons are negative. So if they've got an equal number of each, they cancel each other out. So overall, the charge is neutral. If you gain another electron, suddenly you've got a negative overall charge because you've got one more electron, one more negative electron than you do positive proton. So it becomes an anion, negatively charged. So we're going to put in our little electron there. And same for bromine. It goes in with the unpaired electron to create a pair, and overall it will have a negative charge. So our halide ions have a 1- charge. We don't put the 1 because we're lazy, so we just put the minus. Hopefully none of this is new to anybody at any point, but when they form molecules, so when our halogens exist in room temperature and pressure, they exist in molecules. And so as well as forming ions, they can also covalently bond with other elements that need one more electron, or can covalently bond to something that needs at least one more electron anyway. And they can form diatomic molecules with themselves. Atoms of halogens can form diatomic molecules with other atoms of halogens. This bond between the two, so the sharing of a pair of electrons, is what forms our covalent bond. So I'm just going to pop that in. There is a shared pair of electrons. That's not the full definition of a covalent bond. That's just a quick definition. Let's do these guys as chlorine. So that's a chlorine, that's a chlorine. They have a bond between them. These bonds, these covalent bonds, are very strong. So chlorine molecules, halogen molecules, if they are our elemental molecules, so just made up of the same atom bonded to itself, or bonded to another one of the same atom, these have very strong bonds between them. Covalent bonds are strong. So they have strong intramolecular forces. So if you are at university, you may have intramural sports or intra-house competitions, and that is within your house or within your department or whatever. So intramolecular means within molecules. So intramolecular forces mean within molecules. So these intramolecular forces or intramolecular bonds are, in this case, covalent, between our chlorine atoms. We will come to it more later, but don't forget there are also intermolecular forces between molecules. So we have intramolecular bonds within the molecules and intermolecular forces between molecules, but we'll come to that a little bit later. The intramolecular bonds are strong. Okay, let's keep going. So quick definition, if you weren't sure at the beginning of this of today what the definition of a compound is. A compound is a substance that results from bonding between two or more different chemical elements. So some molecules, such as Cl2, can't be classed as a compound because it's only got a single element. It's only made up of a single element. A compound is a substance that results from bonding between two or more different chemical elements. So ionic substances can be compounds, covalent substances can be compounds, as long as there are two or more different elements within that compound. Hopefully you know that. I mean, I think lots of the time we cover this at Key Stage 3, but it's good to go back and practice it and make sure you're confident. So these are some examples of compounds that group 7 elements can make. We can make something ionic because they're right over on the right-hand side, so very easy to gain an electron to become an ion. Right-hand side of the periodic table, so really easy to gain an electron to become an ion and therefore form an ionic substance such as sodium chloride. Or we can form covalent molecules such as HCl. Now HCl is in this case going to be polar covalent, or it's covalent bond but with a difference of electronegativity. We'll come back to that later. And oops, let's just put that in. So we will have a polarity difference across the bond between the hydrogen and the chlorine, or if you wanted to draw it out like that, you could. But like I say, we will come back to that later on. Don't forget as well, at any point, you can be messaging Facebook Messenger or emailing the email that was at the beginning of this session to make sure, you know, to get all of your questions answered. For now, what was I doing? Oh, yes. In this case, both of these substances are soluble. So they both form ions in aqueous solution, and that's to do with the difference of polarity. But again, we will cover that in a little bit more detail a little bit later on. So let's have a quick go at an exam question on this content. It says, draw a dot and cross diagram to show the bonding in these two species. So thinking about our context, command words and directions. The context is dot and cross diagram, so that's bonding and structure. That's the area of the topic I'm thinking about. But I could take some of the direction to be a little bit more specifically bonding in HF gaseous and bonding in HI aqueous. So already I'm thinking, right, okay, so I've got a gaseous, something that's gaseous, so it's going to be a molecule. HF gaseous must be a molecular HF because it's formed a gas as the molecule. And HI aqueous, so that substance has dissolved, so likely an ionic substance, therefore. So just little things to think about. So that's my context. Oops, didn't mean to do the draw. Context is dot and cross diagrams. My command word is draw. So I've got to come up with a drawing. And then my directions are specifically these guys here. What am I looking for? And something that actually I hadn't necessarily flagged, but it would be worth flagging, is that in terms of this as an exam question, why have they asked it? Why have they asked this of us in an exam situation? The difference is that we've got HF and HI. So there are different elements in there, but what effect has that had? That's had an effect such that I'm looking at HF in the gaseous context and HI in the aqueous context. So what might the difference be between these gas and aqueous solution, the bonding within these substances? That's one of the things, just as a quick aside, please feel free to go ahead and do those dot and cross diagrams. But just as a quick aside, one of the things I try and do when teaching is to get students to think about why have they asked this question? If you can understand why an examiner has asked this question, it often leads you to the answer. So, you know, if you can work out why an examiner might have asked an exam question, it might be because they want to know that you can tell the difference between X and Y. They want to know that you can explain this in a new context. If you can understand why they're asking it, sometimes it can lead you to an answer which can be quite useful. So in this case, why are they asking it? Well, because they want to see if we can tell the difference between the bonding in these two substances. What is the difference? So let's have a go. If you have already, brill. But we said if it's HF gaseous, it's likely to be molecular. And if it's molecular, it must be covalent. So hydrogen here is acting as a non-metal, bonding with fluorine, a non-metal. Hydrogen is behaving as a non-metal. We know hydrogen can be a bit weird sometimes, but it's gaseous, so it must be molecular covalent. So let's just put that in. Molecular covalent. If it was gaseous, if it was just, can't think of an example. If it was gaseous sodium metal or something, then it wouldn't be molecular covalent. It would just be a gaseous metal. But in this case, it's a compound that is gaseous. So it can't be anything other than molecular covalent. It can't be a giant structure and be gaseous, because if it was gaseous, we'd have to break all the bonds. So it's got to be molecular covalent. So if it's covalent, we're drawing a covalent bond. So if I was going a dot and cross diagram, you can include circles if you want. That's absolutely fine. You don't have to though. You can, so I'll do both and then you can pick which one you prefer to do. But hydrogen and fluorine are bonded to one another. Hydrogen only needs 2 electrons in its outer shell. It's got 1 as a valence electron, so it can gain a second one. Fluorine has got 7 electrons in the outer shell. It wants to gain 1 more to get 8. So if they each share 1 electron, they've both got their full outer shells. So I'm going to show that by drawing the dot and cross where my circles cross. And then I'm going to fill in the rest of my fluorine's electrons just to make sure I've shown the full outer shell bonding. If they ask for all of the shells, obviously make sure you include all of them. If they don't, you can just include outer shells, and they should be happy with that, unless you've made an error, obviously. So you can do it like that, or if you didn't want to do, so I'm just going to draw that to say you can do either. If you didn't want to draw your dots, your circles, you could just do it like that, and that would be absolutely fine. The only issue with not drawing circles, if you have a much more complicated diagram you're doing a dot and cross diagram of, it therefore can make it harder to determine where the electrons belong. So just do what you think is going to be clearer for you in an exam. HI, what about the bonding in HI? So again, because it's aqueous and it's a substance, it's dissolved. So it's very unlikely that it is dissolved in water as a complete molecule. Technically it could have, but because we know that this is hydrogen, which can behave as both a metal and a non-metal, and iodine, which can behaves as a non-metal, the likelihood is, therefore, this is way, way more likely that this is going to be ionic. And again, that's why they've asked me this question, because there is a difference. They don't just want me to draw 2 lots of dot and cross diagrams that are with covalent bonding. They want me to draw a dot and cross diagram for covalent and a dot and cross diagram for ionic. It makes sense, therefore, that the answer must be ionic. And if it is ionic, how do we draw that? Well, hydrogen behaves as a non-metal, so gives up an electron, so actually has no electrons in its outer shell. So I can draw it with or without the circle, but no electrons. And that means it has an overall positive charge. And iodine has gained 1 electron. I've done a small iodine for some reason, never mind. Has gained 1 electron from the hydrogen. So each iodine atom will have gained 1 electron from each hydrogen atom. Hence, it's a 1-to-1 ratio, and it will have an overall charge of -1. I've drawn the gained electron as a circle. You can do it the other way around. It doesn't matter. But if they've asked for a dot and cross diagram, you should have at least 1 dot and or cross of each. And if you want to add in extras like triangles to show electrons that are coming from outside, that's fine. You won't get penalized if you do or don't. But as long as you've got at least a dot and or a cross in your diagram, sorry, dot and a cross in your diagram somewhere, then you'll be fine. Okay, let's have a think about atomic size then. So there's a lot of this theory that can be applied to all the other groups. We're obviously going to apply it to the context of group 7, but like I say, the theory is the same across the groups most of the time. So in this case, atomic size, moving down a group of the periodic table, atomic size will always increase. So this is across the board. As you go down group 1, group 2, we'll ignore the transition metals for now, group 3, group 4, group 5, group 6, group 7, group 8, the atomic size will always increase. If we plotted the halogens, the first 4 halogens on a graph against atomic radius, so that's radius is from the center to the outside of an atom, then we can see that they get bigger. So we start off small, getting a bit bigger, getting a bit bigger, getting a bit bigger. So that's our atomic radius increasing. There we go. Why is this then? As you go down a group, why is there increasing size? Have a think. I will just say, again, one of the things that makes memorizing some of this content or recalling some of this content hard is because lots of places will show you all of the trends in terms of increasing. Lots of places will show you all of the trends in terms of always going from left to right across a period and top to bottom down a group. And because of that, sometimes your trend could be increasing, sometimes it could be decreasing, or sometimes you could be going bottom to top up a group because you're always doing increasing. It just means the trends are always the same, but the way that you're told to remember it or the way it's introduced to you might be the opposite to the way that you started memorizing it. It's one of the things that makes chemistry really difficult. I will do my best to always talk about trends going from left to right across a period. So there could be either decreasing or increasing across a period, left to right, and down a group always. I will do my best so that it's consistent, but just bear in mind you may have been taught it in terms of always, where does the increasing trend go? Does it go from right to left, or does it go up the group if it's increasing? So just bear it in mind. It can be confusing, and sometimes we do mix the two up. What else did I want to say? Oh yes, so why is it increasing in size? It's increasing in size because as you go down period, one of the links to the periodic table is every period, so 2, 3, 4, 5, etc., you are adding a shell of electrons. So moving down a group of the periodic table, atomic size will always increase as we are adding another shell of electrons. So E minus, I'm just using as electrons because I'm lazy. In an exam, please write it out as the full word electrons, but I'm just being lazy for now. Electrons, so we're adding another shell of electrons for each period. The period number tells you the number of shells of electrons in that atom. Okay, let's have a think specifically. So here we've got fluorine, bromine, and iodine. We're thinking about single atoms of these rather than them when they're in their molecular elemental state. Fluorine has got 9 electrons in total and is that size. Chlorine has got 17 electrons in total and is that size. Bromine has got 35 electrons in total, and iodine, I can't actually remember how much it's got. We'd never be asked to draw iodine though. Oh, actually, to be fair, iodine gets confusing, so we'll leave that for now. Okay, lovely. And where are their outer electrons then? Where are the outer electrons? So for the first 3, those are the ones you might be expected to write the electron configuration for. So actually, you're unlikely to be expected to write the electron configuration for bromine, I don't think, but you might, so we'll keep practicing. So where are those outer electrons? All of these are what we call p block elements because their outer electrons exist in a p orbital. So all of these have their valence electrons in p orbitals. So if we were writing out the electronic configuration, fluorine's outer subshell would be 2p5. Subshell notation would be 2p5. So 5 electrons in the p subshell. In shell 2, the second p subshell. Chlorine would be 3p5, bromine 4p5, iodine therefore 5p5, but we'll leave that one for now. So we can see every time we're adding a shell of electrons, that is increasing the atomic radius. Why? Just have a think, we'll come back to it later, but why is the atomic radius increasing when you add a shell of electrons, as well as the electrons being added further out? Why are they added further out? What's happening between electrons that are present and ones you're adding that means that they sit further away? Just have a think. We'll come back to it. Okay, what about going across a period? As we go across a period from left to right, this is left to right, atomic size decreases. Let's see what that looks like. So as you go across from left to right, there is decrease. Oops, that doesn't look like a word. Decreasing size. Atomic size decreases. And you can see that, for example, as we go from lithium to neon, from sodium to argon, you can see the atomic size decreases. You can even see it from hydrogen to helium. We have a decrease in size as you go across the period. So why is that? Why? We've just looked at when we're adding extra electrons, it gets bigger. So why, when we're adding extra electrons here, is it getting smaller? This is something that confuses lots of students. It's because as we go across, as well as if you're going from one element to the next element, as well as adding an electron, we're also adding a proton. And the effect of adding a proton, because protons are positive and the electron is negative, the effect of adding the proton pulls in the other electrons a little bit tighter. So moving across the period, atomic size decreases as we are adding an extra electron. or no, let's say it differently. As we are increasing the number of protons, let's say it like that. Increasing the, again, I'm going to be lazy, no number of protons. But we are adding the electrons into the same shell. If we're adding the electrons into the same shell, adding the electron into the same shell as previously, I'm going to write there, the same shell. If we're adding it into the same shell, then that shell is already being provided with shielding. We're not increasing the amount of shielding because the electron's going into the outer shell. If the electron's going into the outer shell, then it's not going to be adding any shielding. So by adding the electron to the same shell, so there is no added shielding. If there's no added shielding, but we've added a proton, the electrons are pulled in tighter. Electrons are, I'm going to say held in tighter, but you can also say there's a greater attraction between the protons and the outer electrons. Hence, the atom is smaller. Okay. One thing that you can see really beautifully as well, sorry, in this graph is just the jump up when you add a new shell. Because the outer electrons now have shielding, are now being shielded by a layer of electrons effectively between them and the proton. So you can see there as well, and there's a new shell added, so there's increased shielding. The other way to think about it as well, just to link back to our the slide before, is the shielding, as well as being kind of a shield, a layer between the outer electrons and the proton, it's also repulsion. If I'm adding electrons to the outside, I know that the orbitals are not technically within rings like we think about them, but if we're adding an electron to the outer shells, there's added electron repulsion. And that is going to cause the size of the atom to increase as well, because the electrons are going to be repelling. Although the outer electrons are attracted to the nucleus, they're also going to be repelling the inner electrons as well. There's another way to think about it, another way to help understand the theory. Okay, let's have a go at some exam questions. Oh, there's a fly. So this says, state and explain the size difference between fluorine and sodium atoms. Atoms, not molecules. So context, I'm thinking about size difference between atoms. So that's structure and bonding. State and explain the size difference. So my command word is state and explain. I've got two. So the likelihood is we're going to get this 3-mark question. So we're going to get 1 mark for the statement and 2 for the explain. It's important to think about that because you want to make sure that your explanation includes 2 markable points. If you've only given 1 part of an explanation, you can only get 1 mark for the explain part. So you'd lose a mark. So make sure that your explain has got 2 parts to it or 2 awardable pieces of information. So state a simple answer, explain, give reasoning. And then specifically, it's between fluorine and sodium. So why have they asked us this question? It's another example where we can think, why would they have asked us this question? Fluorine and sodium. Think about where fluorine and sodium are on the periodic table. So why have they asked us this question? Why is it important or interesting? What answer would you give? Have a think about what answer you would give here. And then we will have a look. I'll give you 10 seconds or so while I take a drink. The other thing to note as well, actually, I'll say is questions like this are usually expecting you to compare the 2 atoms, and therefore you need to think about using comparison words as well. Now, often they'll use the word compare in their questions, so compare the size difference between fluorine and sodium, and in which case you need to definitely make sure you're using comparison words. So things like bigger than, or more than, or whatever. So you can't just say that there are a large number of, because that's just a statement of something on its own. You have to say that there is more than, so that it's a comparison between 2 things. Anyway, what would we say here? So something like this. If we're looking from fluorine to sodium, we would be thinking about our increase in the number of protons. So as you go from fluorine to sodium, there is an increase in the number of protons. This is going to draw the electrons in tighter, or you can say the attraction between the protons in the nucleus and the outer electrons will be stronger, or there will be a greater attraction. There's an increase in the number of electron shells as well. So we go from fluorine down to sodium. We've added an electron shell. That means there is greater shielding. You can also talk about there being greater electronic repulsion between electrons, but shielding is usually the word they're looking for in an exam, the word shielding. Overall, the electron repulsion effects, so the shielding, is greater in sodium, which causes an increase in its atomic size. Compared to fluorine. So that's our comparison in there. 3 marks available. The first mark is to state the size difference. So we've actually put that in our final sentence, which is fine, where we've said it causes an increase in its atomic size compared to fluorine. So that's our first mark, or a mark. Then 2 marks for the explanation. You'll notice that we've got the, what's the word? We've got the, we're looking at both sides of the arguments here because both sides are important. There's an increase in the number of protons which draws electrons in, but actually we've said that the atomic size is increased. That's why this is a 3-mark question and not just a 2-mark question, because you've got these two conflicting ideas. The idea that you're adding protons, so that's going to draw them in tighter, but you're also adding electron shells, so that's going to allow an atom to be bigger. And so 1 mark will be for stating both of those facts. The increase in the number of protons draws them in tighter, or would make it smaller, but then you've got an increased shielding, which allows it to be bigger. And the second mark, for the explanation comes from the fact that we've said the electron repulsion effects, or the shielding effect, so you could have said shielding there, effects are greater. If they are greater, if they have more of an impact on the size, then that's what causes the difference in size. So we've had to say both sides of the argument, but we've explained which is the dominant factor. Okay, let's keep going. So electronegativity, again, something we can link to the periodic table, which I think we probably will do shortly. But electronegativity, so definition of a covalent bond. Again, there are a few definitions out there. They do differ amongst exam boards. Some of them are given to you in your exam board specification, so check. But a covalent bond is a strong electrostatic attraction between a shared pair of electrons and the nuclei of the bonded atoms. Something along those lines will work perfectly. The key is that it's the strong electrostatic attraction between a shared pair of electrons. Okay, so that's a good key point. That's why we put it in bold. And the nuclei of the bonded atoms between them. Or around it, sorry. So learn it if you can. Learn that definition, or learn the one from your textbook, but be aware that there are differing ones out there and on the internet. Just learn one and just keep reminding that one. When you come to do an exam question, don't Google it and use a different one. Use the one that you've been trying to learn. Make sure you're only learning one thing when you need to. But yeah, so what's happening in covalent bonds? Why are we talking about electronegativity? Well, if we've got, let's go back to blue. If we've got HF, so just as we've got this diagram here showing us our electron-rich region and our electron-poor region, if we draw HF there and show it in terms of a dot and cross diagram, our shared pairs of electrons. So dot and cross, we've already looked at this one, so I won't explain it too much. But what's actually happening? Is that exactly where the electrons can be found or not? What is this term electronegativity that Pauli came up with? We need to know the definition because we need to be able to give it in an exam. So electronegativity is what? How do we determine it? Negativity. Just double checking my spelling. Is what? Electronegativity is the ability of an atom to attract to attract the pair of bonding electrons, so it is a pair, bonding electrons. Again, I'm going to be lazy and do E minus, but please in an exam write out the full word. In a covalent bond. You need to learn that off by heart because we need to be able to give it. But what does that mean? How does that affect things? Why does that create this electron-rich region and an electron-poor region? Let's have a think. So if they're supposed to be sharing electrons, but most of the electrons are spending, because the shared pair of electrons, between hydrogen and fluorine, are actually spending more of their time around the fluorine than around the hydrogen, then hydrogen, which has only got one proton, and so only needs to share, has got one electron that belongs to it, so is neutral with that one proton and one electron. And fluorine has got 9 protons and 9 electrons. Yes. So when it's got 9 protons and 9 electrons, it's neutral overall. So when we combine in a covalent bond, a hydrogen and a fluorine, our structure is neutral. There are the same number of protons as electrons. But fluorine has got, if the shared pair of electrons between hydrogen and fluorine actually spend more time around the fluorine because they're more attracted to the fluorine, the hydrogen is left with just its single proton. It no longer has control or exists with its electron, and so becomes delta positive, partially positively charged. That means it is an electron poor region, so it's delta positive. Fluorine has therefore got control of, or an extra electron is spending more time around fluorine than it has protons. And therefore, fluorine becomes an electron-rich region, or delta negative. Okay, so let's think about it in terms of these species. So protons in the nucleus, we've just said this, protons in the nucleus draw all of the electrons in the atom towards them. Of course they do, they're attracted. Protons are positive, electrons are negative. Therefore, as you increase protons, if you're increasing protons, you're going to be increasing the electronegativity, the ability to attract protons towards them. Protons in the nucleus draw all of the electrons in the atom towards them. So in general, and I'm saying in general because it's not an exact science, chemistry never is, adding more protons increases electronegativity. Increases electronegativity. However, and we'll think about how that applies to the periodic table in a minute. However, if we add enough electrons to fill a shell, what's going to happen? Well, our bonding electrons will be further from the nucleus. So our valence, our available electrons for bonding, will be further from the nucleus, our outer electrons. And therefore, because we've added a shell, more electrons will be shielding the nucleus. That means as you go down a group, you're increasing protons, which should increase electronegativity, but you're also, as you go down a group, increasing electron shells, which is going to reduce electronegativity, decrease electronegativity. So again, in general, this decreases electronegativity. Oops, definitely haven't given myself enough space. Let's try that again. Electronegativity. I'm so sorry for my handwriting. Electronegativity. So, which has the impact then? Again, we're thinking all of this, it's both sides of the argument, positives and negatives, advantages, disadvantages, for and against. In lots of cases, there are conflicting bits of chemistry that we have to be confident about which is the dominant factor. And I know that I found it difficult when I was doing my chemistry A level of trying to remember which is which. Here's a little hint. It's nearly always shielding. Shielding is the dominant factor, nearly always. So if you're ever unsure and you haven't got it sorted in your head, just guess shielding, because it's nearly always shielding is the dominant factor. So that will be what the trend that you see appearing. So in this case, it's the same. It is shielding. So overall, that doesn't look like a word. Let's try that again. Oops. Overall, the dominant factor is shielding. As in, that has the greater effect, and that is what trend we see. So what trends do we see then in our periodic table? As you go across a period from left to right, again, I'm just going to show that I mean from left to right. I'm trying to keep it consistent. The number of protons increases, electrons being added to the same shell, and that means electronegativity increases. Electronegativity increases across a period from left to right. What about as you go down a group then? As you go down a group, although you are increasing number of protons, you are also increasing the number of shells, which increases shielding. And shielding is a dominant factor, so we can ignore the effect of the protons and just concentrate on the effect of the added electron shells. So as we go down, electronegativity decreases. Although it is important to recognize that protons are added, and so the trend that you see is lessened by the fact that you are still adding protons as you go down a group. So if you weren't adding protons, you were just adding shells, you'd probably see a greater decrease in electronegativity as you went down a group. But because we have got additional protons as well, that decrease is lessened because the protons are trying to increase electronegativity a bit. You'd never be examined on that, but I do think it's important to recognize. One of the ways, my favorite way to remember this trend, so rather than having to remember again 2 different facts, the trends and what direction the trends are going in, etc. Just remember, what's the most electronegative element? You've probably been told a million times. What's the most electronegative element? Fluorine. Fluorine is the most electronegative element. So if you're looking for trends, you know that fluorine has got to be the top of the trend. It's got to be the highest. And therefore, everything must be increasing towards, across the period, it must be increasing towards fluorine, and upper group, it must be increasing towards fluorine, or it must be decreasing away from fluorine. So if you can remember fluorine is the most electronegative, I will write it out fully, electronegative, then that helps you to remember the trends, because that's got to be the top, the most within the trend. Let's keep going. So using these trends, we can explain why reactivity decreases down the group. So reactivity of the halogens decreases down the group. And we can explain it using our reactivity. Fluorine is the most reactive halogen because of its electronegativity. So fluorine is the most reactive halogen, as it is the most electronegative. So its ability to grab an electron and hold on to it is means that it can steal electrons from things, so it can react as an ion easily, but also it forces things to share electrons with it loads, because it wants that bonding pair of electrons, it wants to attract that bonding pair of electrons. That means it can form stable products, and that's one of the reasons why it reacts. Fluorine is also the smallest. Why will that mean that it's more reactive? Why does being small mean it's more reactive? It means the product that it forms when it steals an electron has a very high charge density. So has greatest charge density as an ion. As you go down the group, the atomic radius is going to increase. If the atomic radius increases, charge is spread across a greater area. And halogens are trying to gain an electron when they react. So the bigger the atom is, the lower the charge density is of the anion that would be formed, and therefore linked to that, the harder it's, let me rephrase it, the attraction between the outer electron and the nucleus is going to be weaker. So you're not going to create an anion that is as stable. Okay. Did I want to say anything else? Don't think so. Okay, let's go. So let's have a go at some answers. How am I doing for time? Not too bad. Might speed up a little bit. So exemplar exam questions. Actually, no, we're doing right. Exemplar exam questions is a short answer. By considering the trends in the properties of group 7, predict the following for astatine, stating a reason for each. So what's the question about? The context is properties of group 7. So in my head, I'm thinking group 7 properties, right? What do I know? What do I know about that? The command word, I need to predict something and state something. So my command words is state and predict. So predict, that tells me, and hopefully should reassure me, that I shouldn't know this off by heart. Because I've been asked to predict something, the meaning of the command word predict, as we looked at before, is that you shouldn't know it, but you should use the information you're given to work it out. So predict the following for astatine. I don't need to know it, but I can work it out. I have been given the tools as an A-level chemist to work it out. State a reason for each. So give a short reason for each. They don't want long sentences because it's just said state, so a short reason for each answer. And the direction, well, I've been asked about the trends in properties, so physical state of astatine being at the bottom of the group. So as the trend changes, what will the physical state of astatine, what is it likely to be? Its atomic size and its electronegativity. It says relative to other halogens. That's an important point because it hasn't asked me to predict the Pauli number for it, its electronegativity value for astatine. So I don't need to think about actual exact numbers. I just need to think about the trend because it's relative to the other halogens. So is it going to be more or less electronegative than the other halogens? Okay, so physical state at room temperature. What would you have said? As we go down the group, gas, liquid, solid, well, astatine can only be a solid then because iodine was, and that's above it within the trend. So it should be solid. Why is it solid? Why is it going to be solid? It's solid because we've got, and we're going to look at these a little bit more in a couple of slides time, but we've got more electrons in astatine. That means we're going to get stronger intermolecular forces relative to the other halogens. That's our explanation. More electrons, sorry, that's solid, that gives us our first mark. And then the explanation, there are more electrons, so stronger intermolecular forces for the second mark. What about B? What's its atomic size compared to other halogens going to be? Well, as we go down the group, we've added shells. Yes, we've added protons, so that usually pulls the electrons in, but we've added shells, which adds shielding. Shielding is a dominant factor, so that's why it's getting bigger. So it's larger because there are more electron shells. And I'm just going to add in and more shielding, and therefore more shielding. If you want to add another layer of explanation to it, so say it's a 3-mark answer, not a 2-mark answer, you could then go on to say, and therefore more shielding. So the attraction between the nucleus and the outer electrons will be weaker or less. So if you have the marks available and you need to give complete explanations, you would go on to say more. This is just stated a reason, so I don't need to go into too much detail, and there's only 1 mark available for it anyway. So there's no point in me giving 5 or 6 layers to my explanation. I wouldn't get any more than 2 marks. Part C as well, then, explain its electronegativity. Well, again, we know the trend is decreasing electronegativity as you go down the group because fluorine is our most electronegative element. So it must be less electronegative. Why? What's going to affect its ability to attract an electron in a bond? Well, if it's miles away, it's not going to be able to attract it very strongly. The attraction between the nucleus and the outer electrons is going to be very weak. because of the added electron shells. So astatine is less electronegative as it has more full electron shells that shield the outer electrons from the nucleus. In both of these cases, C and B, so I'm just checking A as well, but in C and B it's more pertinent. There are contradictory things that we could have said. So we could have talked about increased number of protons attracting electrons and pulling them closer. But because, again, thinking about what are they looking for, why are they asking us this question, it's only a 2-mark question. So all they're interested in is, can we explain the trend, not can we justify the difference in size or anything like that. Can we compare? We're not looking at both sides of the argument. They're only interested in a short answer. So I only need to give one side of the argument. Again, thinking about what are the examiners looking for? Why are they asking us that question? Okay, let's keep going. So group 7 molecules. Let's go back to our molecules and think about intermolecular forces. So as we said before, halogens have 7 electrons in their outer shell, therefore they form simple covalently bonded diatomic molecules. They have strong covalent bonds, let's do chlorine again, between the atoms within the molecule, but they also have weak intermolecular forces between the molecules. So let's do those in orange. So personally, when I'm talking about bonds, such as metallic bonds, ionic bonds, and covalent bonds, I like to use the word bond. When I'm talking about an intermolecular attraction or an intermolecular force, I try to use the word force. For me, that helps me to think bonds are stronger than intermolecular forces, so it reminds me of that bit of theory. But also it helps me to differentiate between when I'm talking about intermolecular forces, so between things, or intramolecular bonds. So for me, I try and keep that separation in my head. So intermolecular forces are weak. They're still present and they still have an impact, but they are weak. So there are strong covalent bonds within the molecules, but weak intermolecular forces between molecules. What do we call these in halogens cases? What are our intermolecular forces in the case of a halogen? What would we call them? We can be more specific about our intermolecular force if we're asked. Hopefully, you would know they're called London forces. Now, this is another point of contention, I know, for students when they're doing revision, because you'll see van der Waals written everywhere, all over textbooks and revision guides and all across the internet. And your teachers, you might even have learnt about van der Waals. Now, across the exam boards, they prefer you to use the term London force, because a London or dispersion force. Or you can be specific and call it an instantaneous to induced dipole attraction. So instantaneous to induced dipole attraction. That you can use any of those phrases, London force, dispersion force, or instantaneous to induced dipole attraction. They are all, those words, those phrases are interchangeable. The word van der Waals is actually a little bit more of an umbrella term, which includes our London forces, but also actually technically talks about other things as well. So here, if we're talking about specifically an instantaneous to induced dipole attraction or force, we want to call it a London force, not a van der Waals. And that's why I think they changed it in the specification. Pre-2015, they called it van der Waals. They could just use the umbrella term van der Waals. Now they want us to be a little bit more specific. What was I going to say? Right, so London forces. These are London or dispersion forces. Can't spell. Dispersion forces. Again, you might see them as van der Waals, so I'll put it in there, but we shouldn't really be using that term. And they are weak, so they require only a little energy to overcome. This explains what property of halogens or group 7 molecules? What property would this explain? It explains our relatively low, and relatively, because it's comparative, relatively low melting and boiling points. Melting points and boiling points. MP, BP, melting point, boiling point. Again, it's relative because compared to, for example, metals often have melting points that are in the hundreds, if not thousands. Our halogens, even though iodine, for example, is solid at room temperature, it's still got a low boiling point compared to, low melting point compared to lots of metals, for example. So we say that it is low. Even though technically it's solid at room temperature, we'd still say it's a low boiling point. Okay, cool. So let's just do a quick overview of the intermolecular forces because we've already spoken about some of them. So here, our hydrogen bonds are the strongest type of intermolecular force. There are three that you will have learned about or that you will talk about: hydrogen bonds, dipole-dipole interactions, or permanent dipole-dipole interactions, and our London forces. Hydrogen bonds are the strongest. Now, van der Waals is what I was saying earlier. Van der Waals is actually an umbrella term which includes permanent dipole-dipole interactions and London dispersion forces. Now, London dispersion forces are the weakest, so let's add that in. So these are our strongest type of intermolecular force. These are the weakest type of intermolecular force. Hydrogen bonds are strongest. London dispersion forces are weakest. Now, within our van der Waals umbrella, we can talk about our dipole-dipole interactions and our London forces. And within dipole-dipole interactions, there are actually, again, two kinds. One which you may have spoken about and one which you may not. So these dipole-dipole interactions could either be between two permanent dipoles or between a permanent dipole and an induced dipole in a neighboring molecule. So again, this is why when we're doing chemistry, we have to be so specific with our word use. Do you mean to talk about van der Waals as an umbrella term for all of these other interactions? Or did you mean specifically London forces? What is a London force? We're going to talk about it specifically a little bit more in a second. But the other way you might have heard them described is an instantaneous dipole to an induced dipole. I can't spell instantaneous. Instantaneous to induced dipole-dipole attraction. Think about what those words mean. If it's instantaneous and it's interacting with an induced dipole, what does that mean? With our dipole-dipole interactions in the middle, the one that you probably are more comfortable with talking about is the permanent dipole-dipole interaction. Or when you've been taught it, you might have just been taught about dipole-dipole interactions as an umbrella term. Fine. Just be very careful, like I say, that when you're talking about something, if it doesn't matter, you can just use the term dipole-dipole interactions. But if you're talking about a specific permanent dipole interacting with another permanent dipole, then you need to use the term, you need to call it permanent to permanent. But yes, most of you will have either spoken just about dipole-dipole interactions or about specifically permanent dipole to permanent dipole interactions. Okay, hydrogen bonds are the strongest. What is a hydrogen bond? I'll just add that in super quickly. How do we determine a hydrogen bond? I think we look at it again a tiny bit later in one of the exam questions, but we'll look at it now. What is a hydrogen bond? How do they form? It's the attraction between a, why have I gone orange? I didn't mean to go orange. To go red. It's the attraction between a delta positive hydrogen, so a partially positively charged hydrogen, and the lone pair on a very electronegative element. The lone pair, LP, lone pair on a very electronegative element. Try and get my spelling right. Negative element, specifically oxygen, nitrogen, or fluorine. If oxygen, nitrogen, or fluorine isn't attached to that hydrogen, to a hydrogen, that hydrogen won't be delta positive enough. That's when hydrogen bonds form. Okay, so if you've got an oxygen, a nitrogen, or fluorine attached to a hydrogen, that's making it delta positive enough. And oxygen, nitrogen, and fluorine also have lone pairs. Those lone pairs are able to be attracted to a delta positive hydrogen in a neighboring molecule. So those are the key aspects. Okay, cool. Let's keep going. So intermolecular forces, let's think about these London forces. So if you've got a non-polar molecule, by that I mean a molecule which has no polarity across it. So molecules we would class as being non-polar, then they don't have a permanent I'm just going to talk about non-polar molecules. So if they are non-polar, then what interactions can you have between other molecules? We're only going to get London dispersion forces. Oops, didn't mean to press that button. Let's go blue again. London or dispersion forces. Acting. How do they form? Or why do they happen? This is a nice I have seen exam questions where they ask you to describe how a London force arises. So how does it rise? The constant random movements of electrons. We draw them in electron shells and we draw them in bonds, but the reality is they're moving all over the place. It's just these shapes are where we are most likely to find a pair of electrons, or most likely to find an electron. So the constant random movement of electrons leads to the formation of instantaneous dipoles. These instantaneous dipoles induce dipoles in neighboring molecules. These induce dipoles so they cause a dipole to occur in neighboring molecule by attracting or repelling an electron. Molecules by attracting or repelling electrons. And the force of attraction is stronger when you've got more electrons within the molecule. If you've got more electrons, you can have a bigger dipole. You can have a bigger dipole, you can have a greater charge difference. If you've got a greater charge difference, you've got greater attraction. So the force of attraction is stronger the more electrons they are. So moving down group 7. What's happening? They've got more electrons. More electrons as you go down group 7. Therefore, we're going to have moving down with more electrons, therefore stronger London forces. No, let's go back a step. Stronger London forces. What does that mean? That means they therefore require more energy to overcome. And what does that impact? It impacts the melting and boiling point. Higher melting point or boiling point or boiling point. So the more electrons you've got in a molecule, the greater the dipole can be, and that means the greater the attraction to other molecules can be, and therefore the more energy is required to overcome that attraction, and therefore higher the melting point or boiling point. Just be careful with the words you use. I like to use the phrase stronger or greater, because when we talk about like longer chain molecules, personally, I think you should then say that there are more intermolecular attractions because of the longer molecule. There's more places where you can have an intermolecular attraction, but when you're comparing molecules, it's actually the size of the attraction that can change as well. So just be really careful with word use, be very specific. So the attraction is stronger, you can say greater here as well. That would be fine. How are we doing for time? Let's speed up a little bit. So I'm not going to have a go through this exemplar exam question because we have basically just done it anyway. And I'm just going to move swiftly on to the next bit of the content just to make sure we get it all covered. So again, feel free to have a go at this in your own time, and we will send over the answers afterwards when you complete the feedback. So let's have a think about reactions of halogens. I'm just going to take a drink. One of the things that I think students find quite easy to remember, but you do still need to remember, so if you haven't memorized it yet, get it learnt, is testing for halide ions in aqueous solution. So how do we work out which halide ion is present in a solution? There are a couple of steps. You need to do all of them, and you need to understand all of them as well, why they're important. first we need to add dilute nitric acid. Then we need to add a few drops of aqueous silver nitrate solution. And then we can, if we need to, add dilute and then concentrated ammonia. Why? Why are all of these steps important? So specifically your reagents are just dilute nitric acid and then aqueous silver nitrate solution. But why do we need the nitric acid? What's the point of it? So dilute nitric acid, that is HNO3 aqueous, that's nitric acid. What's the point of it? We're about to add in aqueous silver nitrate. So why are we adding in the acid? What does the acid do? Hopefully you're aware that basically the reason that this test works is because it forms a precipitate, and we can therefore work out the color of the precipitate, hopefully. But actually, it's not just the halide ions that form precipitates with nitrates, with silver nitrate solution, sorry. There are other things that would form a precipitate as well, because silver compounds, lots of them aren't soluble. Carbonates would form precipitates, and so would hydroxides. So we add in nitric acid to counteract or to get rid of any carbonates or hydroxides that could affect our test. Nitric acid will react with carbonates and hydroxides. Think about what might be formed, because you should know it, or we should be able to work it out. The nitric acid will react with carbonate ions or hydroxide ions, removing them from solution or removing them from the reactivity equation, and therefore meaning we won't get any false positives. It can react with any carbonate, as in CO3 2-, or hydroxide, as in OH- ions present. So therefore removing them from solution. Removes them so that they can't react with our silver to form the wrong precipitate or an incorrect, a false positive. Carbonate plus acid makes carbon dioxide and water. So we get carbon dioxide given off and water left in solution. That's fine. Hydroxide reacts with acid. Well, that's just an acid-base neutralization. You just form water. Again, we're fine with water. So by adding in some nitric acid, you can get rid of those ions. We can then add in our drops of aqueous silver nitrate solution, and we will get a precipitate. So Ag plus forms a often coloured precipitate. I'm going to use PPT to mean precipitate in the future because I'm lazy. So aqueous silver nitrate solution is AgNO3 aqueous, sorry, I meant to write that in. So Ag plus in the silver nitrate forms a coloured precipitate with our chloride, iodide, no, let's do bromide next, sorry, bromide or iodide. The nitrate, the reason we use nitric acid and the reason we use silver nitrate is because all nitrate salts are soluble. So the nitrate will stay in solution whatever happens. And that means that we're only ever going to get, therefore, we've gotten rid of the carbonate and the hydroxide, so we're only ever going to get precipitates from our silver chloride, silver bromide, or silver iodide. Perfect. Oh, I still need to whiz on. Hurry up, Alyssa. So add dilute. Why do we add dilute and then concentrated ammonia? What's the point? We add them because this is, oh, sorry, I forgot to say, this is AgCl, this is AgBr, and this is AgI. I'm ever so slightly going to go into our break here. Apologies. And our precipitate colours are white, cream, and yellow. We need to know these off by heart, so make sure you learn them. Why we add dilute and then concentrated ammonia? Why would we? What's the point? Hopefully we know it's because if you add dilute ammonia, AgCl is soluble in dilute ammonia, but AgBr is not. So if we take my precipitate, let's say it's a mixture of AgCl, AgBr, and AgI. AgCl is soluble, so will dissolve. So if it's, for example, a mixture of AgCl and AgI, the AgCl will dissolve. But AgBr and AgI won't. If we then add concentrated ammonia, AgBr is now soluble in concentrated ammonia. Excuse me. So if my precipitate dissolved in concentrated ammonia but not dilute, I'd know it was AgBr. And then AgI is insoluble in both, so it stays as a precipitate. So it's another way of proving what compound you've got. Okay, there's a little bit of a summary table here, which I'm just going to fill in really quickly and then take a drink. And then we are going to go over, apologies, by probably 4 minutes just to fill in the disproportionation reactions on the next slide before we have a break. So let's just fill this in really quickly. So Cl minus forms AgCl precipitate when silver nitrate is added, and the color is white. Need to remember that. AgCl is soluble in dilute ammonia, NH3. So if you have got silver chloride and you want to prove that it's silver chloride, you can add a little bit of dilute ammonia and it will dissolve. Lovely. Silver bromide solid is formed on the addition of silver nitrate to bromide ions. That is cream. Notice the color gets more intense as you go down the group. That's how I remember it. Again, rather than remembering each individual one, I remember the trend because it's a little bit easier for me to remember it. And this is soluble in concentrated ammonia. So if I add dilute ammonia and it doesn't dissolve, but then I add concentrated ammonia and it does dissolve, I know it's AgBr. And iodide forms AgI soluble, which is a yellow precipitate. And that is insoluble in ammonia. So if I've tried dilute ammonia and concentrated ammonia and it hasn't dissolved, it must be AgI. And this is useful because the difference between white and cream can be a little bit hard to distinguish sometimes, or the difference between cream and yellow, or even sometimes the difference between white and yellow in a precipitate can be hard to determine. So we can prove which silver halide salt we've got by using ammonia solution. Okay. Let's just finish off with our disproportionation reactions, and then I will let you have a break. Apologies. So this is one of the reactions that is kind of unique, or not unique actually, is important when thinking about halogen reactions. And this is disproportionation. What is disproportionation? Can we remember what it means? Disproportionation is when a reactant is both oxidized and reduced in the same reaction. There's a couple of different examples. Some are not required for some examples, so I will highlight it in a second. So our reaction of chlorine with cold water, so chlorine, Cl2 plus water, goes to make what is formed. We need to know these off by heart, so you either need to understand where it's coming from or you need to learn these. So we form HCl and HClO. If you know it's a disproportionation reaction, you can kind of get there towards the answer, because we should be able to determine the oxidation states. Chlorine starts as 0 because it's an element. Elemental oxidation states are 0. So Cl2, the chlorine in Cl2 is 0. The chlorine in HClO and HCl, however, are different. In HCl, hydrogen is +1, which is its normal state. So chlorine is -1 to cancel it, to balance it, to make it overall neutral. The oxidation state in the perchlorate bit is oxygen is -2, because it's nearly always -2. Hydrogen is +1. That means our chlorine has to be +1 as well. So if we look at it, our chlorine has gone from 0 to +1 and from 0 to -1, so it's been both oxidized and reduced. Why is this useful? When is this used? This is used to disinfect water. This is why we talk about adding chlorine to swimming pools and stuff. It's used as a water disinfectant. What about with a cold alkali then? Chlorine with a cold alkali, Cl2, NaOH. This is technically a reversible reaction. What's formed? Notice it's a similar reaction to the one above, in that instead of HCl, we've got NaCl, and instead of HClO, we've got NaClO. And then there's also the addition of water, because, you know, we've got that extra, those hydrogens and oxygens, which need to be dealt with. What's going to happen in terms of oxidation states? Well, we start in 0, NaCl, chlorine is -1, NaClO, again, the chlorine is +1 because the balancing is the same. So again, chlorine in the element is 0, chlorine in NaClO is +1, and the chlorine in NaCl is -1. So again, it's been oxidized and reduced. It's a disproportionation reaction. What's that used for? Well, this is actually how you can make up bleach. So NaClO is found in bleach. Lovely. And hot alkali. Now, oops, if you are OCR, you don't need to be able to do hot alkali, so this bottom one is not necessary. But funnily enough, it's very similar, but it's also, I think, quite interesting. Because if you've got hot alkali, so you've got a little bit of extra heat in that species, in that reaction, we actually end up forming NaClO3, and then NaCl, same as above, and water, same as above. NaCl, and this means, hold on, I'm going to just, rather than working out my balancing, I'm just going to put it in. You can just memorize this if you want, or you can work it out each time. I'm just going to write it in because we're running out of time. So that's a 3Cl2, 6 lots of NaOH goes to make NaClO3 plus 5 lots of NaCl and 3 lots of water. That doesn't look like a 3, but it's supposed to be a 3. And what happens in terms of the oxidation states now? We go from 0 to -1 in NaCl as normal, but here we've got 3 lots of oxygen, so we've got -6 for our oxygens, +1 for our sodium. That means chlorine is going to be +5. So this is where, because we've got the extra heat, we can get a further oxidation of chlorine in this disproportionation reaction. So NaClO3 has an oxidation state of +5, and then NaCl as normal. When is that useful? Let's finish up by saying, again, it's also bleach. So NaClO3 is a compound of bleach, or it can be used as bleach, and in weed killer.